Hey guys, today we're looking at 3.2's notes, which is all about linear functions. Our big objective for today is being able to identify when a function is linear and when it is nonlinear from a graph, from a table, from an equation, in a bunch of different ways. So starting off with what we know about linear functions, when you look at the word linear, the word line probably sticks out to you, and that's because all linear functions are straight lines. That's why they're called linear. So all linear functions are straight lines. And we know that they're straight lines because they have a rate of change. Because the rate of change between any two data points is not a constant, a constant value. So if I look between any 2 points, the x values and the y values between those different points, like my inputs and my outputs, change at this constant rate. If we have a constant rate of change, that means my function that I'm looking at is going to be linear. A nonlinear function is a function whose rate of change is, of course, not constant. That means that their graphs are not going to be straight lines. So they could be curved, they could have some bend in some way. Now, don't get yourself fooled, because they could involve straight lines, but that doesn't mean they're not just a straight line. And even there's one in particular that we'll take a look at that is just a regular straight line that's actually not a linear function, but that's more so because it breaks the rules of being a function in the first place. But we'll get to that in a little bit later. All right, so let's take a look. If we're trying to figure out if something is linear or nonlinear, again, our rule, or what we're looking for, is if we have a constant rate of change, meaning that my x values and my y values change at a constant rate. So from a table, which we could also be given a set of points, we could be given a mapping, as long as we can find what those points are. What we want to do here is look, as I look at my table, do my x values change at a constant rate, and do my y values change at a constant rate? So going from one row to the next in my table, I'm just going to look and see, all right, to go from 2 to 4, what is my change? In this case, I'm going up 2. If I go from 4 to 6, that again is adding 2. 6 to 8, I'm adding 2. So you can see here, in this case, my x values are changing at a constant rate. For my y values, going from 50 down to 35, that would be subtracting 15. 35 to 20 is another subtraction of 15. 20 down to 5 is once again a subtraction of 15. Now for this, all they're asking us for is to determine if it's linear or nonlinear, and to explain, which our explanation here, I'm not going to spend some time on it, because basically an explanation for all of these could and should be really the same thing. Yes, it's linear because it has a constant rate of change. No, it's not linear because it does not have a constant rate of change. So I'm not going to write the explanation on all of these. Just know that it's the exact same thing. So here, because my rate of change is constant, it is linear. In the explanation again, we have a constant rate of change. If we look at number 2, now again, just looking for my x values and if they're consistent, and my y values being consistent. So here I go from 1 to 4, which is adding 3, 4 to 7, adding 3, 7 to 10, adding 3. So I can see my x values are still changing consistently, which is good. For my y values, however, 1 to 16 is adding 15, 16 to 49 is adding 33, 49 to 51 is adding, 49 to 50, or 100 is adding 51. So we can see that even though my x values are changing consistently, my y values are not. So this, in this case, this would be a non-linear function because the rate of change is not constant. If I can spell here, constant. And again, those answers could be the same and really should be the same for all of these. Yes, there is a constant rate of change, so it's linear. No, it's not a constant rate of change, therefore it is nonlinear. Now, what I did here on number 2, in order for you to be able to say definitively that it is nonlinear, I do need to make sure my x values are changing consistently. Because if my x values aren't changing consistently and my y values aren't changing consistently, that doesn't necessarily mean it's not linear, because we could have gaps in my points, or we could have some uneven spacing of my x values, which could then account for having missing points and stuff. So like if I had a point where, like in this left one in number 1, if I ignored that 4 and 35 value, if I had that row just missing and it was 250, 4 or 620, 85, you would have inconsistency in both x and y, but that doesn't necessarily mean it's not linear. So something to look out for. In these, you need your x values to be consistent no matter what. And then if your y values are also consistent, it's linear. If your y values are not consistent, then it's not linear. All right, getting into graphs, which for these ones should be the easiest one for all of us, because here we're just looking at, hey, is this a straight line? Yes. Cool. Awesome. It's linear. Is it not a straight line? Is it curved? Does it bend? Does it change directions at all? Oh, it does that thing? No, it's nonlinear. And that really is it. So for my graphs, you can see again what they look like. The one exception, so kind of the special cases here that I'll then highlight here. Something that breaks our rules for functions. If we have, let's go ahead and do our coordinates here, coordinate plane. If our graph was a straight vertical line, we would say that this is not a linear function, because it's not a function in the first place. This is not a function. It fails vertical line test. So that's why we would say it's not a linear function. So you have to be careful on kind of how it's phrased. If they ask you, is this a linear function, and it's not a function, then you have to say no, regardless of whether it's a straight line. In this case, it is a straight line, so that part of it makes you think it's linear, but because it's not a function in the first place, that means it's not a linear function. But that's really the only exception to the rule. Horizontal lines are still fine, and then any kind of, obviously, lines with any kind of slope to them are also linear functions. The part that's probably the most challenging for most of us is going to be looking at our equations, because there's a lot of different ways our equations can look. Really what we need to focus in on is when it's linear. So in this case, when it's linear, this is one of the ways that it can be written. It's probably the one you're most familiar with slope-intercept form, which is something we'll talk about in later sections for this chapter. But really the important thing here, in order for it to be linear, once you have y by itself, so with all of these, you have to first get y by itself. Because before you can do anything and say, yes, it's linear, no, it's not linear, you have to have y all the way by itself, which is where that early chapter 1 skill comes in, where we were solving those literal equations and rearranging for y. That's where they come back in here. That's why I felt they were so important back in chapter 1, even though they were so different from what we were doing. Now we're seeing it come back for us. So once we have y by itself, in order for it to be linear, x has to be just x to the first power. It can't be in the denominator, so in the bottom of a fraction. Just regular x to the first power. That's it. No square roots, no other exponents on it. You can see here the ones down below with quadratics and cubics. We have these other exponents happening on my x values. Even though they do have x to the first power involved in them, we have to make sure that the only thing happening in our equation is x to the first power. That's the only place we see x, is just to the first power, not in the exponent, not in the denominator, just at the main level, no funky stuff happening. Then we get to say it's a linear function. Anything funky happening to x, or if x is in a weird location that you're not used to seeing, that tells you it's not linear. So let's take a couple look at these. Take a look at a couple of these, is how I should have said it. So for these examples, for A, B, and C, we're asked to just identify whether this is linear or nonlinear just from the equation. And again, we're looking at, is this just regular x to the first power, nothing else funky happening? With number A, y equals 4x, yes, this is linear. I'm just going to write L, linear. For part B there, on the right side of the graph, or the right side of my page here, now in the middle and on the left side, if y equals x squared plus x minus 2, y is by itself, but we can see here that my x has a squared on it, even though the typeface here is a little bit blurry. We have something happening to x besides just x itself, so this would be a non-linear function. And then for part C, y equals 7 over x. This again is one of those times where I wrote up there, if x is in the denominator, if it's not just x to the first power on that main level, it's not going to be linear. So in this case, even though it is just x all by itself, x to the first power, because it happens in my denominator, it's actually not a linear function. It's nonlinear. So those should be our conclusions for A, B, and C. Take a look down below here. These ones are going to be a little bit more tricky. For this one, for number 1, this one's extra tricky because I don't see an x value in here. But if I look at what my equation would graph, if I go ahead and just do a little sketch here, yep, y equals 5 would be a horizontal line at 5. Y equals 5 would just be right there, up 5 units. So in this case, it actually is a linear function. What's tricky about this is that I could rewrite this as y equals 0x plus 5. Because it actually is a line, which later on this will make sense. It's a line with a y-intercept of positive 5 with a slope of 0. It's a flat line just straight across. So that's why I don't see my x value in my equation, but it is still a linear function. Tricky, but it's linear. Okay. For number 2. Number 2 here, we're asked to identify if it's linear or nonlinear. Before we can make any conclusions, looking at this, I think it's linear. It looks linear to me. We've got x just in their main level to the first power, so nothing else really funky happening. But again, in order to guarantee that it is linear, we have to get y by itself first. So we're going to go ahead and solve this equation. So if I want y by itself, I'm going to subtract 2x from both sides. That gives me 3y equals negative 2x plus 10. I divide by 3 all the way through, and I get y equals negative 2/3 x plus 10/3. So even though I've got fractions and stuff kind of happening on the right side with my x is still just to the first power. It's not in the denominator. It's not anything else funky happening. So this is indeed linear. Our initial kind of gut reaction to this was correct. Okay. Number 3, pretty straightforward. X is squared, nonlinear. Y is already by itself. Number 4, this is the reason why we have to get our y by itself, because if you look at this, x is just to the first power. It's not in my denominator or anything like that. But if I was going to solve for y, I have to make sure I get y by itself. That would mean I have to divide by x on both sides to get y by itself. So I end up with this equation, y equals negative 13 over x, which x is in my denominator, so that means it is actually a non-linear function. So you have to be careful with those, non-linear. All right, that is from an equation. Going to the back side, these ones, really easy, really straightforward. From a graph, they're all visual. Again, I don't need necessarily an explanation on these. Or again, if I do require one, or if the homework requires one, the answer really should be the same. Hey, this is linear because there's a constant rate of change. Hey, this is nonlinear because there is not a constant rate of change. And that could be your explanation for every single one of these. So basically, anything that has a curve to it, that it's bent, or anything like that, is nonlinear. Anything that is just a flat or straight line is going to be linear. So here, just doing these quickly, A is going to be nonlinear. D is going to be nonlinear because both of those have curves to them. They're not just straight lines. B is linear, and C is also linear. And those ones, again, B is that horizontal line, even though it is flat and straight across. It doesn't have any curve to it, or any not curve. It doesn't have any angle to it. It is still a linear function. It still passes the vertical line test. It is a constant rate of change. It's just that in this case, that rate of change is going to be 0. All right, last one, word problem. So in this one, for part E, the frequency y in terahertz is of a light wave is a function of its wavelength x in nanometers. Does the table represent a linear or nonlinear function? And explain. So even though there is kind of a context to it and it looks overly complicated, with some big numbers, my process on identifying if it's linear or nonlinear is still exactly the same. I'm still going to look at my x values. Is there a constant rate of change? Is there an equal space between all of them? And then for my y values, again, do they follow a constant rate of change, or is there some variation in that? So I'm still going to go ahead and start with my x values. I want to make sure there's equal gaps between these. So you'll probably have to use a calculator for these. Don't feel ashamed that you have to do that. I would rather you be safe than sorry on these, especially with big numbers like this one with our word problem. So we're going to have to try and figure out, going from 660 down to 595, what was my change. And in this case, I'm just going to go up here instead, just the little space that I have. That was going down 65, from 595 down to 530. That was down 65. 530 down to 465. So to do this, to find what that rate of change is, you do your second point minus the term that came before it. So in this one, what I'm doing here is 595 minus my 660. That tells me what I have to do in order to get down to 595, in case anyone was not picking that up, or in case I didn't say that earlier. So 465 minus 530 is also negative 65, and then of course 400 minus 465 is a negative 65. So you can see there is an equal gap between all of my x values, and that being decreasing by 65. Doesn't matter what that change is, because we're not asking anything about that, just is it linear or nonlinear. So far, we're looking good. It's constant. For my y values, though, to go from 454 to 504, I would have to add 50 to get from the first to the second. But to go from 504 to 566, that's actually going to be adding 62. So if you get to this point, you don't necessarily have to find all of the spaces between all of them. If I'm looking to see if it's linear or nonlinear, I know my x's are consistent, and I already see an inconsistency in my y values. You don't have to figure out how inconsistent it is. As soon as you identify that it's not consistent, you get to go ahead and say, oh, it's nonlinear. The rate of change is not constant. If I can spell again, constant. So without having to do anything else, as soon as you see that inconsistency going from 50 to 62, without having to see the rest of it, you know that it's going to be nonlinear. It doesn't matter what happens for the rest of it. My x's were evenly spaced. My y's were not evenly spaced. Therefore, it's nonlinear. So that's all I got for you guys today. Homework is down there on the screen. It is page 117 and 118, 6 through 26, just the evens. As always, if you have questions, concerns, thoughts, or ideas, make sure you guys are reaching out and letting me know. I'm available during class if you finish it now, or during office hours from 2 to 2:45, or via email at any point during the day. I'm glad you guys watched, and hope everything goes well. If not, I'll see you soon.